Hi, this is Group 1 from the Tuesday 12 to 3 lab section's video report on the flow field and drag analysis of a circular cylinder in Cal Poly's low-speed wind tunnel. There are many real-life applications of flow around cylinders. Fluid flow around cylinders is seen on the landing gear of airplanes, structures of spacecraft upon entry and re-entry, and even on everyday items like the necks of golf clubs. In most cases, engineers study the flow around cylindrical objects in order to reduce the effects due to drag. Increases in surface roughness will increase the thickness of the boundary layer and move the separation point closer to the stagnation point. The separation point is controlled in man-made objects such as the landing gear and golf clubs by minimizing the cross-sectional area, which minimizes the effects of flow separation. The materials used are also smooth, minimizing the effect of the surface roughness on the separation point. The landing gear is also often stowed away in the plane when it is not in use, which reduces the amount of time the cylinder is exposed to flow. This creates less drag, allowing for more efficient flight and a faster swing. One unique characteristic phenomenon of circular cylindrical flow is vortex shedding. Low-pressure eddies known as vortices form due to airflow around the cylinder. The flow regime of these vortices is highly dependent on Reynolds number, as illustrated by the diagram shown. These fluctuating low-pressure regions can result in forces on the body. These forces can lead to structural issues such as vibration as well as acoustic noise. A common metric for describing the effects of fluid flow around a blunt body such as a cylinder is the coefficient of pressure. Coefficient of pressure is a dimensionless unit for pressure within a flow field. It is an excellent way to analyze pressure distributions without regard to the size of the body being analyzed. Pressure coefficients from experimental data are calculated using equation 1 shown. This can then be compared to the theoretical approximation for inviscid flow, which is calculated using equation 2. Comparison of experimental values to the values gained from equation 2 can also give insight into whether the flow is laminar or turbulent. The team had multiple objectives for this experiment, including using pressure measurements around the face of the cylinder to find and analyze pressure drag coefficients, utilize flow visualization to visibly qualify boundary layer separation, and explore how these results can be changed by altering either the Reynolds number or by tripping the boundary layer and inducing separation. Prior to running the lab, the team decided to run the experiment at 2 Reynolds numbers, one high and one low. The team was given the constraint to maintain wind velocity speeds within the wind tunnel below 30 meters per second, which is why a maximum RPM of 600 was selected. A Reynolds number coinciding with a low wind tunnel speed of 100 RPM was chosen for the sake of clear flow visualization. The experiment took place in Cal Poly's low-speed wind tunnel. The cylinder was placed toward the front of the test section as illustrated in the figure shown. The length of the cylinder was equal to the width of the test section and fixed to the walls of the test section. The cylinder used for this experiment was 0.1208 meters in diameter and 1.1557 meters in length. It was equipped with 24 pressure ports surrounding the circumference of the cylinder. There were 15 degrees of separation between each pressure port. The cylinder was oriented such that the stagnation point was located at pressure port 14, shown in figure 6. For the second half of this experiment, a tripwire was positioned and secured approximately 40 degrees from the stagnation point between ports 11 and 12 in order to trip the boundary layer, inducing early flow separation. The team chose to use a tripwire as the means of tripping for multiple reasons. The first reason is that attaching a tripwire at an ideal spot would guarantee flow separation, whereas altering a property such as surface roughness through the use of sandpaper or something of that sort would possibly not be as effective. The location of the tripwire is also easier to alter. The team ran into this problem during the first attempt at using a tripwire. The tripwire was placed too low at approximately 20 degrees above the stagnation point, and after the initial boundary layer separation, the flow was able to rejoin with the cylinder. The wire was then moved further from the stagnation point and resulted in a fully separated boundary layer.
Before running the wind tunnel, ambient pressure and temperature values were recorded. These parameters were monitored over the course of the experiment, and variations of 1.2 degrees Celsius and 0.8 hectopascals were noted. The testing period elapsed 1 hour and 20 minutes. The team began this experiment by conducting a formal safety check and clearing the tunnel of any loose debris that could inhibit testing per the safe working procedure. While this was completed, team members also collected ambient temperature and pressure readings. A sample rate of 100 readings per pressure port per data collection period was selected within the scanning valve interface. At this time, a full set of wind-off pressure data was recorded without the wind tunnel running for calibration purposes. The wind tunnel was then set to 100 RPM and started up per the safe working procedure. A settling period of approximately 15 seconds was allowed prior to recording any data. Once this settling period was complete, pressure readings were collected. Once pressure readings were completed, the smoke machine was then positioned at the inlet of the wind tunnel as shown in Figure 9. The location of the smoke machine was adjusted until optimal flow visualization over the cylinder was achieved. At this point, flow visualization was recorded and then the smoke machine was removed from the inlet of the wind tunnel. This process was then repeated at 600 RPM. The wind tunnel was then turned off so that the boundary layer tripwire could be attached to the cylinder as previously indicated. Ensuring that it was properly secured, both pressure data collection and flow visualization were once again completed at 100 and 600 RPM. Once all necessary data was collected, the wind tunnel speed was reduced to 0 RPM and the tunnel was turned off. Final wind-off pressure readings were taken and the experiment was complete. At the lower Reynolds number, the smoke is much closer to the top of the cylinder than it is at the higher Reynolds number. Also, the vortex street is fairly visible and would probably be much more noticeable with a high-speed camera. At the higher Reynolds number, the smoke can be seen further vertically from the top of the cylinder, and the vortex street is not seen anymore. In the case of a high Reynolds number with no tripwire, we see the boundary layers beginning to transition from laminar to turbulent. By this time, however, the vortex street is mostly, if not fully, turbulent. At the Reynolds number we ran this part of the experiment at, both these flow characteristics match up with what is generally accepted. While turbulent, the wake remains wide and somewhat organized. The smoke can also be seen sticking and wrapping around the top of the cylinder as the wind flows over it. With the addition of the tripwire, flow separation occurs further up on the cylinder due to the surface roughness it adds, and the smoke detaches from the cylinder closer towards the front of the cylinder than it did with a no tripwire case. Here the team has plotted pressure coefficient on the y-axis and position around the cylinder in radians with 0 degrees at the stagnation point on the x-axis. The team is comparing the pressure data collected in the wind tunnel to a predicted and viscid solution of pressure coefficient is equal to 1 minus 4 times sine squared theta. This solution is unrealistic for multiple reasons, noting mostly that it implies 0 drag. A trend can be noticed that the real data matches up closely to the inviscid solution on the front side of the cylinder, about from negative pi over 2 to pi over 2, but does not represent pressure behind the cylinder very well at all. This is because a Kármán vortex with very low pressure is created right behind the cylinder. Here the team has plotted the pressure readings with and without the tripwire attached. The pressure coefficients seem to be much lower behind the cylinder in the tripwire case because the flow separation earlier on in the cylinder creates bigger vortices behind the cylinder due to its blunt body.
Since the length of the cylinder used in testing reached both walls of the test section, it can be approximated as a cylinder of infinite length. With this assumption, the team expected to find coefficients of drag of approximately 1.2. However, the values calculated were 0.27 at 100 RPM and 0.25 at 600 RPM. This results in a very high error. However, the coefficients of pressure do decrease with the introduction of a boundary layer trip. This trend was expected because the boundary layer trip induces flow separation, therefore reducing the overall drag force acting on the cylinder. The main source of error in the experiment is due to fluctuations in the flow of the wind tunnel. These fluctuations are caused by recirculation, the 90-degree angle of flow from the vents that supply the air to the intake, a door being opened while we were taking data, and slight variations in RPM due to wobbling in the belt that runs the fan. This creates up to 5% error in the data. Other, less impactful sources of error are error due to slight changes in the ambient conditions during testing, and error due to measurement equipment, such as the slight protrusion of the pressure ports that disrupts the flow, and error in the scanner valve system. The use of a sphere in this experiment would yield a coefficient of drag value that is much lower than that of a cylinder. Where cylinders have a coefficient of drag of approximately 1, spheres are around 0.5. The cylinder used in the experiment reached both sides of the tunnel, allowing the team to make the assumption that the cylinder had infinite length, thereby creating two-dimensional flow over the portion of the cylinder with the pressure ports. The flow is disrupted near the walls of the tunnel due to boundary layer effects, but the ports are far enough away from the boundary layer that its effects are negligible for the pressure readings. Since the edges of the sphere would not reach the end of the wind tunnel like the cylinder does, the effect of three-dimensional flow would have to be taken into account. This will make the flow more susceptible to being asymmetric. The surface roughness would have an effect on whether the flow is symmetric. Slight variations in the roughness of two opposing sides, as well as any imperfections in the sphere, will create an uneven flow field. This is not as much of a problem in a cylinder because the flow only passes above and below the cylinder. The sphere would have to be symmetrical all around in order to create a symmetrical flow regime. Overall, the main focuses of the lab were using pressure measurements around the face of the cylinder to find and analyze pressure drag coefficient, utilizing flow visualization to visibly qualify boundary layer separation, and exploring how results changed by altering the Reynolds number and inducing separation of the boundary layer close to the stagnation point. These were successfully accomplished through the course of this experiment. The team was able to confirm that flow field visualization and the phenomenon of vortex shedding is highly dependent on the Reynolds number of the fluid. After collecting pressure readings, the team was also able to calculate pressure coefficients, illustrating that as Reynolds number increases, there is an increase in the coefficient of pressure. The team also found that inducing boundary layer separation closer to the stagnation point will result in higher magnitudes of pressure coefficients downwind of the tripping point. If this experiment were to be run again, there are multiple steps the team would take to reduce error and gain even more insight into weight characteristics and drag pressure around the cylinder. With the gained experience of this initial experiment, the team now has the knowledge to create further developed lab procedures and scenarios to enhance the team's understanding of the flow field and drag effects around a circular cylinder, which include such ideas as increasing the range of fan RPMs tested and collecting data at more frequent intervals within the test section.